Hello friends, welcome to UGC EPG Pathshala. I am Anamika, Senior Research Fellow, Birla Institute of Scientific Research, Jaipur. Today I am going to discuss application of remote sensing in watershed management. This whole lecture contains various topics related to watershed management. They are introduction, application of remote sensing in watershed management, watershed characteristic, morphometric parameters, drain patterns, use of remote sensing in dam site selection, identification of submergence area, water volume calculation, objective of watershed management programs. Now first come to introduction part. The word watershed, introduced in 1920, was used for the water pardoning boundaries. A watershed, also called a drainage basin or catchment area, is defined as natural hydrological unit which converts specific areal expansion and area of land surface from which the runoff flows to defined drain, channel, streams or river at any particular point. Watersheds are considered more efficient and appropriate unit for assessment of resources and subsequent planning of sustainable development of resources, because land and water resources have optimum interaction and synergetic effect. The watershed approach is therefore increasingly being employed in various development programs in India like soil and water conservation, command area development, erosion control, forest management, desert development programs, river valley project, flood prone area management, reclamation of wasteland, etc. From the hydrological point of view, the different phases of hydrological cycle in the watershed are dependent on the various natural features and human activities. Watershed is not simply the hydrological unit but also socio-political ecological entity which plays crucial role in determining flood, social and economical security and provides life support services to rural people. The image of watershed is given in figure number 1. Now come to the application part. Application of remote sensing in watershed management. Remote sensing and GIS technologies are direct application in watershed delineation, surface water inventory, mapping and calculation of watershed properties, morphometric parameters, resource mapping and assessment, watershed prioritization, slope evaluation, soil mapping and land suitability, runoff generation, resource utilization, conservation and management, strategies for watershed development, etc. These technologies are also used in deserts like flood assessment and post-flood action planning. Watershed delineation. By applying watershed tool, the watershed are delineated for any basin, catchment or specific area with the parameters. The hydrologic modeling tool in the ArcGIS Spatial Analysis Extension Toolbox provide method for describing the physical component of a surface. The hydrologic tools allow us to identify sinks, determine flow direction, calculate flow accumulation, delineate watershed and create streams networks. The image number 2, we can see this watershed management technique. A resulting stream network derived from an elevation model, watershed delineation is achieved using DEM streams, slow flow direction, etc. parameters which we can easily see in figure number 2, 3 and 4. Surface water inventories. High resolution near infrared sensors such as those on Landsat, IRS and other satellites can be used to measure the extent of surface water. Numerous results for satellite study indicates the water bodies even of very small area can be delineated on satellite images through digital processing. Now come on watershed characteristic. In general terms, in more compact watershed, the runoff hydrograph is expected to be sharper with a great peak and shorter duration. For a watershed that is partly long and narrow and partly compact, the runoff hydrograph is expected to be a complex composite of the above mentioned hydrographs. Morphometric analysis of watershed. Morphometric analysis of watershed is necessary to understand complex interrelation of linear, aerial and relief aspects of terrain in any watershed area. For this purpose, database of various parameters of drainage such as coding, ordering, flow direction and land surface like slope, elevation, extent, etc. are calculated. Analysis of morphometric parameters are calculated and tabulated. Stream order, stream length, drainage density, stream frequency, bifurcation ratios, shape index, circulatory ratio etc. are calculated. To hypothesize the approach for water resource development planning, remote sensing and GIS techniques have potential to calculate following morphometric parameters using a various tools and application models such as length, area, elevation differences, runoff calculation, automated method of drainage ordering and so on. Following morphometric parameters are important for watershed management. First is linear aspect. Linear aspect contains stream order and stream length. Mean stream length ratio, bifurcation ratio, relief aspect, relief ratio. And the third one is aerial aspect. Aerial aspect contains only drainage density. The second one is stream ratio, third is stream frequency and the fourth one is form factor. Fifth is circulatory ratio, sixth is elongation ratio, seventh is overloaded flow. Now we come to the first, linear aspect. Linear aspect contains stream order. Now what is stream order? Stream order is as a measure of the degree of a stream branching of a stream within a watershed. First order stream are defined as those channels that have no tributaries. In this case, the flow is depending entirely on surface overland flow to them. The junction of two first order stream forms a second order channel. When a low order stream segment joins to the high order stream segment, then the order of the stream remains as it is higher order. Second order channel receives flow from the two first order channel that form it and form overland flow from the ground surface and might receive flow from another first order channel that flow directly into it. Third order channel is formed by the junction of two second order channels. It receives flow not only from the two second order channels that form it but also direct overland flow and possibly from first order channel that flow directly into it and possibly from other second order stream that might be join it. In general, an nth order stream is a tributary formed by the two or more stream of order n-1 and streams of lower order. Numerical ordering begins with the tributaries at the stream head water being assigned the value 1. Automatic drainage ordering can be done using software as seen in figure number 6 and figure number 7. Stream length and mean stream length. Generally, total length of a stream segment in first order stream found maximum and decreased at the stream order increases. Stream strength is a combined function of length of slope, rock structure and rainfall intensity. The smallest streams measured in first order are located on the crest while the longest measure is located on the valley floors. Generally, higher the order, longer the length of the stream is noticed. Mean stream length of any order is greater than that of the lower order and less than that of its next higher order. Length of individual stream of any order can be calculated through GIS tools as seen in figure number 7. Stream length ratio. Ratio of the main stream length of the one order to the next lower order is stream length ratio. In general, this factor increases from lower to higher order. The decreasing trend of mean stream length ratio shows that the terrain is undulating and area has many streams and generating complex streams. Configuration of all orders. Higher order stream are low in compared to lower stream order, therefore this factor in higher order is high. Once the stream length is calculated through GIS software, it is easy to calculate stream length through normal arithmetic, which we can easily see in figure number 7. Bifurcation ratio. It is defined as the ratio of the number of streams of any order to the number of streams of the next highest order. Value of this is indicated by RB, theoretical minimum of 2 or around 6. The division ratio is calculated as is seen in figure number 7. Relief aspect, relief ratio. It is defined as the elevation difference between the reference point located in the drainage basin. Maximum relief is the elevation difference between the highest point and the lowest point. Maximum basin relief is the elevation difference between the basin outlet and the highest point located in the perimeter of the basin. It is easy to compute minimum, maximum elevation and absolute highest and relative relief, which in turn give us relief ratio, which we can see in the given equation. Aerial aspect. Drain density. Drain density is indicative of closeness of spacing of drainage channel. It is factor of total length of streams of all order per unit drainage area in a watershed. Density factor is associated by climate, types of rocks, relative relief, infiltration capacity of soil or rocks, vegetation cover, surface roughness, land and runoff intensity index. It denotes how densely a watershed or basin channelized in a specific area. High value of drainage density are indicative of a stable drainage system and low altitude but undulating. Topography. Area of watershed, micro watershed and stream length of each order can be calculated in GIS used for calculation of drainage density, which we can see in figure number 8. Stream frequency. Stream frequency is the total number of stream segments of all order per unit area. The pattern of stream frequency is generally similar to the drainage density in the watershed because numbers of drainage lines are proportional to the length of drainage lines as shown in figure number 7. Now come on drainage texture. Drainage texture is relative spacing of drainage lines. It is the total number of stream segment of all order per perimeter length of that watershed. Infiltration capacity is important factor influencing drainage texture, which broadly depends on the drainage density and stream frequency. In GIS and remote sensing data, spacing between drainage line can easily be seen. See figure number 9. Form factor. Form factor is indicative of shape of the watershed. High value of form factor shows circular shape and low value shows elongated shape of watershed. It is computed as the ratio of basin area to the square of basin length. Circulatory ratio. It is denoted by RC. It is the ratio of the area of basin to the area of the circle having the same circumference. as the perimeter of the basin. This factor is influenced by length and frequency of streams, geological structure, geomorphic features, land use, land cover, slope, relief, rainfall parameter, etc. High circulatory ratio is indicative of circular shape of watershed. This parameter is helpful in assessment of flood hazards. Higher the circulatory ratio, higher the flood hazards at a peak time at the outlet point, because in circular shape watershed, water drain from almost all direction and meet near to the outlet. As a result, more water is accumulated through all the streams. Elongation ratio. It is the ratio between the diameter of the circle of the same area as the drainage basin and the maximum length of the basin. A circular basin is more efficient in the discharge of runoff than an elongated basin. Higher elongation ratio are indicative of low altitude undulating terrain, whereas low elongation ratio show hilly terrain. Now, overland flow. It is the length of water over the ground before it gets into defined drainage. This factor relates inversely to the average slope of the channel. It is a component of total runoff in a drainage basin. When the rainfall intensity exceeds soil infiltration capacity, the excess water flow over the land surface as overland flow. Length of overland flow is calculated as 1/2 of the reciprocal of the drainage density. Slope of watershed. It determines the flood magnitude and speed of flowing water. Naturally, the steeper the slope of the watershed, the greater the amount of runoff. Soil erosion by water also increases as the slope length increases due to greater accumulation of runoff. The average slope of the watershed can be determined from the topographic map of the watershed by using the following formula. For every small watershed, the average slope can be taken as the ratio of difference in elevation between the watershed outlet and the most distant rise and approximately average length of the watershed L. Driving runoff characteristic. Delineation of watershed or defining stream network include with series of steps. Some steps are required while other are optional depending on the characteristic of the input data. Flow across the surface will always be in the steeper downslope direction. Once the direction is flow out of each cell is known, it is possible to determine which and how many cells flow into any given cell. This information can be used to define watershed boundaries and stream network. The elevation model is used to determine which cell flow into other cell. If this is the case, all water traveling into the cell will not travel out. This depression are called sink. Hydrological analysis tools allow to identify the sink and give tool to fill them. The resultant is a depressionless elevation model by which flow direction on this depressionless elevation model can be determined. Watersheds are delineated by identifying pour point. Usually these locations are mouths of streams or other hydrological point of interest such as a gauging station. Using the hydrological analysis tool, we can specify the pour point or can use the stream network as the pour point. This creates watershed for each stream segment between stream junctions. To create the stream network, we must first calculate the flow accumulation for each cell location. Drainage patterns. The reference to the arrangement of a stream in the drainage basin, which often reflects structural and lithological control of undulating rocks. Drainage pattern tell much about the substances of which the land surface is made. With little practice, interpretation of identification of geological structure and rock type in an area can be met from analysis of stream pattern on satellite images, air photos or topographic map. Major drainage patterns are dendritic patterns, terraces patterns and radial patterns. These patterns can be easily on remote sensing data suitable spatial resolution, which we can see in figure number 11 and 12. Use of remote sensing in dam site selection. Application of remote sensing and GIS technique in hydrology is today is one of the most effective approaches. Recently, remote sensing has provided valuable data sets to examine hydrological variables and morphological challenges over large regions at different spatial and temporal scales. Qualitative criteria implies the identification of suitable valley physical characteristic based on satellite images. Interpretation mainly DEM and large scale available cartography. Other qualitative selection criteria concerns the distance from settlement and infrastructure. Quantitative criteria were based on indexes that synthesize the refractiveness and feasibility of the possible interventions. Submergence area. Advanced practical remote sensing dynamic monitoring method in flood control and hazard mitigation and disaster evaluation. Based on the remote sensing flood monitoring practice, analyze the flow of monitoring flood submergence area, quickly identify using satellite images and develop a spatial radar processing modules in ARDAS imaging software. Using this model, we can easily identify submergence area. Now, water volume calculation. Water reservoirs are the main source of water supply for many settlements as well as power generation. So, the water volume and extent of the reservoir need to be monitored at regular time interval for all efficient use as well as to avoid disasters like extreme rainfall and flood. Generally, the reservoirs are remotely located, so it is too difficult to well monitor the water volume and extent. With the help of remote sensing and GIS modeling techniques, it is probable to monitor estimated ever predicted the reservoir water volume in advance by using the numerical modeling and satellite remote sensing data. Images from different sources like Landsat, TRS and digital elevation model using IRS list 3 and Aster borne thermal emission and reflectance are being used. The methodology involves GIS and image processing techniques such as mosaicing and georeferencing the raw data from satellite, identifying them reservoir water body using the pixel level analysis, calculating area and depth per each pixel. The total water volume calculation are denoted based on the empirical model developed using past validated data. The water spreaded area calculating by using water indexing is covered in the vector polygon using ArcGIS tool. Now, objective of watershed management. It improves production of flood fuel, control of pollution, minimize over exploitation of natural resources, water storage, flood control, checking sedimentation, wildlife preservation, erosion control and prevention of soil and water conservation, employment generation through industrial development, recharging of groundwater to provide regular water supply for consumption and industries as well as irrigation. Recreational facilities for watershed management planning used remote sensing and GIS technique. One can demarcate watershed resources assessment and utilization, need of treatment and can prepare appropriate management plan for the watershed through the following steps. First is delineated and map the watershed boundaries and the smaller drainage basin within the water. Next one is inventory and map of natural resources in the watershed, inventory and map the natural man-made drainage system in the watershed. Next, inventory and map land use land cover map, inventory and map soil maps. Through these techniques, one can identify areas of erosion including stream banks and construction site. Identify the quality of water resources in the watershed as a baseline. Inventory and map pollution source, both point sources and non-point sources. Watershed management programs. Government of India and state governments have many live programs being implemented in the country on watershed management with the objective of soil and water conservation, optimum utilization of natural resources, improvement of flood vegetables, fruit, flooded fuel, etc., mitigation of effects of drought, restoration of ecological balance. For all the programs, Government of India has made it mandatory to prepare detailed project report through remote sensing and GIS technique. Drought prone area program, DPAP. The second one is disaster development program, DDP. National watershed development program for rain fed agriculture, NWDPRA. The fourth one is control of shifting cultivation, World Bank assisted integrated watershed development project. The sixth one is integrated watershed management program, IWMP. And the seventh is Niranchal National Water Project program. Thank you. Hope you enjoyed the lecture.